Hello guys, how are you? I'm Islam, and this is the recorded lecture for the primitives that I told you before. I will record this lecture for you because it will be included in the exam. I think we did many examples in derivative. Let me see in the lecture here. I think we have gone through the lecture with many examples, but I will revise some examples again with you, and I will revise or a quick review for the basic rules of antiderivatives. I think you know very well that if we have a function called f of x, f of x, and when we did a process called differentiation, we get f prime of x or f dash of x. Now here we have the reverse process. If we have f prime of x, now when we did a process called antiderivative, you can say it primitive or you can say it integral. This gives us f of x. So we have the derivative, so we have the derivative that we use to look for in I think there's something. Now we have the derivative, and the objective here is to do a process called antiderivative or primitive to get the original function. So this is the function that if we differentiate this one, we get the derivative of the function. Now, when we try to find the several antiderivative of the function, we have a function f, and when we try to find the antiderivative of this function, we get f, capital F of x plus c. And we said I told you before why we added c to any derivative, because it is to guarantee the all set or the whole set of the antiderivative that if we differentiate these any function from this set, we get the antiderivative. So we get the original function. For example, if I have a function f of x which is x squared, what is the function of the antiderivative? What is the function that if we differentiate it we get x squared? It will be 1 over 3 x power 3. So it is not the only function that if we differentiate we get x squared. No, we can add 1 because the derivative of 1 is 0. So we can add 2, we can add negative 1. So instead of all these constants, we add an arbitrary constant called c. So the family of the several antiderivative is f of x equal 1 over 3 x power 3 plus c. That is the family of the whole set of the antiderivative, that if we differentiate this function, we get the original function. I think you know this very well, but I am doing a quick review on it. So let me give you the three basic rules of derivative, that if you try to initiate any anti-differentiation process or integration or primitive, you will go through these three rules, which are first one, the power rule. If we have a function called f of x, this function is a power function that have a power called n, and we have here n does not equal -1, so this rule we cannot apply this rule when n equal -1. And we have the variable of of integration, which is x. So here we have the derivative of the inside function here. So this gives us f of x to the power n plus 1. You can raise the power by 1 and divide by the new power, which is n plus 1, and don't forget to add c. So this is the first antiderivative rule we will do. So this is the integral sign, this is the integrand, the variable of integration. So any power function, we can do the antiderivative by adding the power, adding to the power 1 and divided by the new power plus c. But we cannot do this if this is not here. We have to check that the derivative is already exist inside the integral. So if we have an example like this one, if I have e power x plus 1 power 5 e power x dx. So we can here apply the power rule because we have a function to the power 5 and we have the derivative of the inner function, which is e power x plus 1. So that the antiderivative or the integral of this function will be e power x plus 1 power 6 over 6. I will say it again. We cannot do this. We cannot do the antiderivative process if e power x is not here. So we have to check very well carefully that the derivative of the inner function, that the function raised to the power 5, is its derivative already exists in the integral. Another example, if we have this function 1 minus x all power 3 dx. So what is the derivative of 1 minus x? The derivative of 1 minus x is negative 1. So we have to check if negative 1 is already inside the integral or not. No, it is not. So we have to add negative 1 here and negative 1 outside. So negative 1 is already exist here as a derivative of 1 minus x, and we multiply it by negative 1 outside the integral because the integral from the beginning is positive, so the negative from outside will stay with us. This is the derivative of 1 minus x. We cannot take this negative outside in the solution, so we can raise the power now to 4 and divide by 4 plus c. So this is the first rule that you have to check if you have any integral to solve. This is the first one. And second one, if I have e to the power f of x, exponential function raised to the power f of x, exponential raised to the power f of x, and we have here the derivative of f of x dx. What is the function whose derivative is this? It's an exponential function. You write the exponential function as it is and multiply it by the derivative. So if we faced an integral in this form, e to the power f of x, and the derivative of the power is already here inside the integral, so the integral will be e to the power f of x plus c. When you try to differentiate this one, you get this integral. So, for example, what is the integral of e power cosine x sine x dx? Here you can see very well that the derivative of cosine is negative sign. So we have here sine, but we need a negative. So multiply by a negative inside the integral and another one outside the integral. So we have the negative from outside the integral, and we have e to the power cosine x as it is. So we cannot integrate e power cosine and put it e power cosine as it is if we don't have sine x. So you have to guarantee that the derivative is already exist inside the integral. What about this example? E to the power root x 1 over root x dx. What is the derivative of root x? Is e to the power root x 1 over root x. What is the derivative of e power root x? The derivative is 1 over 2 root x. So you multiply it by 2 in the denominator, so you have to multiply by 2 up. So 2 here, so it will be e power square root x plus c. So you can see the function here, its derivative is already inside the integral, so you can integrate according to the rule. Number 3, the three basic rule of our antiderivative is a fraction. A function is in the denominator called f of x, and its derivative is in the numerator dx. So what will we do? What will you do if you face a logarithmic function? If you are asked to differentiate len x or len any function, you take the argument inside the len and put it in the denominator and then differentiate it in the numerator. So it will be len f of x. So I will say it again, you cannot do this if the derivative is not here. So let's take an example. 1 minus 1 minus sine x over 1 plus cosine x dx. Here what will you do? We can distribute the integral in 1 dx minus sine x over 1 plus cosine x dx. So integration of 1, what is the function whose derivative is 1? It's x minus, you can apply here the fraction. I have 1 plus cosine, derivative of 1 is 0, and the derivative of cosine is negative sign. So we have here, we need a negative here. So we can put it positive, make it positive, and moving the negative inside. So we have the derivative of the denominator, cosine, which is negative sign. So it's len 1 plus cosine x plus c. So these are the three basic rules of antiderivatives. If you face any example, any exercise, any problem, and you are asked to get the antiderivative or to solve the integral, please check the first three basic rules. Okay, uh, we have another rules. You can check the other rules of antiderivative, which is the derivative of sine, cosine, derivative of sec, derivative of sine, cosine, and cosec, and sec, yes, and sec, and sec square. All these rules are already exist in the slides of our lectures. You can review it from the lecture. Now I think we have many examples in our lecture. Let's try to solve one of them, but let me give you these important rules about inverse trigonometric functions. What if I face this integral square root in the denominator 1 minus f of x, it's a function, squared, and we have the derivative in the power. If we face this form of integral, it will be, yes, sine inverse, or you can write it arc sine f of x plus c. Sorry. Plus c. Okay. If we face the same integral but with negative 1 minus f of x squared dx, it will be arc cosine f of x plus c. If we faced the integral 1 plus f of x squared, and we have the derivative up there, dx, it will be arctangent f of x plus c. If we face the same integral but with negative 1 plus f of x squared dx, it will be arc cotangent f of x plus c. So let's take one example or two. Integral of e power x square root 1 minus e power 2x dx. I think we have this example in our examples in the lectures. You can review it. I think number 20 or 21, I don't remember, but let's solve it. It's a form of sine inverse. You can see here we have e power x and we have 1 minus e power x squared. So we have 1 minus function squared, and the derivative of this function is up there. So it will be arc sine this function f of x, which is e power x, okay, plus c. Another example, if we have 1 plus ln squared x and we have there 1 over x dx. So it's the form of arctangent 1 plus ln x all squared and we have 1 over x. So ln x, this is the function. Derivative of this function is 1 over x dx. So it will be arctangent ln x plus c. Okay, I will leave many examples that we solved in the lecture for you. You can review these examples. I think we solved most of them. Okay, another one. Let's see. Now, these are the basic rules of integrals. We have, I think, till the slide 33 or 32, the slide 32, the end of examples in the slide 32. And I think we solved most of them. Now, we will now show you the techniques of primitives. The techniques of primitives. Now, what if we have this example? Integral of x e power x squared dx, and this example x squared e power x squared dx. How to solve these two examples? The first one is very easy and you should know the solution of the first one, but the second one is not easy for you, I think, for this for the moment. The first one is easy because we have an exponential function. The power function here is x squared, and the derivative of the x squared is 2x. Now we have 2 here, so we have to multiply by half, and then it will be half e power x squared plus c. We have this. Let's see. It will be half e power x squared because we have an exponential function. It's the derivative of its power is already in the function and we need only 2, so we multiply it inside by 2 and outside by half, so we get the it is a direct primitive. It is the second rule, but here we have an x squared, but the derivative is 2x and we don't have 2x, we have already x squared. So what should we do? So we will, to solve this one, we should take integration or primitive by parts. what will we do in the integration by parts? We to perform or to calculate any integral by primitive by parts, we have to split the integrand of the function to two functions. The integrand, we will split it into two functions. One of them is to be integrated and another one is to be differentiated. Let's take an example. Integral of x squared, x e power x. Let's take this first example. So we cannot do this integral and solve it using our traditional rules or basic rules or direct primitives. We cannot do this. So here we do this very simple table. Here we will differentiate and here we will integrate. So we will choose a function of them to differentiate, which is x, is very easy, and when we differentiate it, it will be 1, and when we differentiate 1, it will be 0. E power x, when we integrate e power x, it will be e power x. When integrate e power x, it will be e power x. So let's do the technique of integration by parts, which is multiply this one by this one and add and put a plus for this term, and multiply this one by this one and negative, and this is the sequence of these signs, begin with plus and then minus and so on. So it will be x e power x minus e power x plus c. So it's very easy. X times e power x minus 1 times e power x, which is e power x plus c. Another example. What if x power 3 e power x dx? It will be in this form. When we do our table, it will be differentiation here, integration here. X power 3, its a derivative is 3x squared, its a derivative 6x, its a derivative is 6, its a derivative is 0. Here we put e power x, which is integration is e power x, and it will be endless. So when we do our integration by parts, this times this plus minus plus minus. Okay, so the integral will be x power 3 e power x plus 3x power 2 e power x plus 6x, this is minus, plus 6x e power x minus 6 e power x, don't forget the constant. Okay, another example. What about this one? Ln x dx. Here we have a small problem. Ln x is function to be differentiated, not to be integrated. If I can integrate ln x, I will integrate it directly. And we don't have a direct primitive to ln x. We don't have a direct function that its a differentiation is ln x. We don't have this one. What should we do? What should we do? Ln x is a function to be integrated. So we will solve it by integration by parts. The differentiation and this integration. What the function that will be differentiated? It's ln x, because we can differentiate x ln x as 1 over x. Now, what about integration? Integration, we don't have another function. La, we have a function is 1. Integration of 1 is x. So this times this by plus, and we don't have an end of the end of this table with 0. Every table here ends with 0, so the integration ends with this table, but we don't have this end. So we will do another technique. Focus. We will multiply this one by this one, but with negative integral. So let's see. It will be like this. X times ln x, okay, minus integral, minus because the next sign is minus, and we multiply x by 1 over x, and we integrate this. So it's x ln x minus x times x, it will be dx. So it's x ln x minus x integration 1 x plus c. Okay, let's take another example. Let's take another example. If we have this example, if we have this one, integral of e power x sine x dx. Here we have two function to be integrated and another function to be differentiated. Let's see. I have a very important note here. Please, all these examples from the beginning of integration by parts, all these examples we don't have a direct primitive to these integrals. We don't have a direct solutions, so we have to perform integration by parts. So what here, what is the function that is to be differentiated and what is the function to be integrated? Here you have a choice to take any one of them to be differentiated. I always take sine x to be differentiated because sine x, it's easy to differentiate instead of going through the negative in integration, but the differentiation is easy in trigonometric rather than the integration. Here e power x sine, its a differentiation is cosine, it's easy, and here the integration is e power x. Here the differentiation of cosine is negative sine, and the integration of e power x is e power x. And we end the table here. Why? If you reach to the form of the problem itself, here we have e power x sine x and we have e power x sine x. Stop here and you will know what. So we will multiply this one by this one plus, and this one by this one minus. It doesn't end with 0, so we multiply this one positive because it is the next sign and integrate. So our integration, this one is e power x sine x dx equal e power x sine x minus e power x cosine x plus, and here we have minus times plus minus integral e power x sine x. Let's take a look to this term and this term. We can add to the both sides integration e power x sine x. We get here 2 e power x sine x dx equal e power x sine x minus e power x cosine x. So we have e power x sine x dx equal half, we divided by 2, e power x sine x minus e power x cosine x. Don't forget the c. Okay, you can repeat the example many times to understand it very well. Let's go through another technique of integration, which is integration by substitution. I think the last lecture with you we did the integration by substitution, and I remember very well that I told you that the suitable substitution will be given to you in the examples. So what about the integral by substitution? Let's try a simple example to understand the concept. If we want to try to integrate this one, 2x plus 1 power 3 dx. Here it's very easy because you will say to me that okay, we have 2x plus 1 here, it's a power function, so we need only the derivative of the inner function inside the bracket, so we have to multiply by 2 and the outside by half, so it will be half 2x plus 1 power 4 and divide by 4, and this is the power rule. But here we have another concept, which is integration by substitution. I think that integration by substitution is not necessary in this kind of examples because it's very easy, but it's very essential and very important in many examples. Here we will here we will do the integration by substitution. As I told you before, integration by substitution is not necessary here because it is very direct primitive. But what does integration by substitution do here? Here we can take 2x plus 1 as any another variable called u. When you differentiate u, it's the u derivative, this part of the right hand side will be 2 dx with respect to x. Now let's write the integration by our integration in terms of our new variable. We substitute 2x plus 1 by u power 3, and the x here, when we can take the x here, it will be half du, so it will be half du. So it will be half integration u power 3 du, and you can integrate it directly. 2x, sorry, it will be u power 4 over 4 plus c. Let's write it in terms of x. U is 2x plus 1 power 4 power 4 plus c. This form is like this one. So as I told you, we cannot use, or it is not very necessary to use integration by substitution in these kind of examples, but it's very essential in many examples. Let's take one of these example like this one. If you ask it to integrate x power 2 over x minus 2 dx, we will take tu squared equal x minus 2. Don't worry, you will be given to this this substitution will be given in the exam. So when we differentiate, it will be 2u du here dx. Now let's write our integral in its form. X squared, from where we can get x squared? From here. X is equal u squared plus 2. So x squared, it will be u squared plus 2 squared over x minus 2, it will be u squared dx, it will be 2u du. So we have written the integral in terms of u instead of x. Now this bracket will be u power 4 plus 4u squared plus 4 over u squared 2u du. Now we can distribute u power 4 over u squared, it will be u squared plus 4u squared over u squared, it will be 4 plus 4 over u squared, all this with respect to u to du. Now we can integrate this very easily. It will be u squared plus 4 plus 4 u power negative 2 to u power 3 over 3 plus 4u plus 4u power negative 1 when you raise the power by 1 over negative 1 plus c. And you can put the integral or the solution in terms of x by substituting u by the terms of x here. So here u is equal to square root x minus 2. So this is the basic idea of integration by substitution. You are taking a part of the integrand to differentiate it, like this one. If you use u squared equal e power x minus 1, we will give you the suitable in substitution, and when you differentiate it will be u, differentiate it will be 2u du equal e power x dx. So it will be 1 over integration e power x minus 1, it will be u squared dx. From here dx is equal 2u over e power x du. Let's have a look again. If we want to take dx, we will divide by e power x. So we have dx here, but we want dx in terms of u, not e power x. So we substitute by e power x here. It will be u squared plus 1. So it will be 2u over u squared plus 1 du. And you can substitute it into the integral. We can erase or cancel the x and put 2u over u squared plus 1 du. Now this can cancel this because it is u squared, and under the square root it will be u. We can cancel u with u, so we have 2 out there and we have 1 over u squared plus 1 du. Remember this very well, it's arctan. So to arctangent ud, sorry, plus c. Now we can write it in terms of in terms of x. It will be square root e power x minus 1 plus c. From here you get u e square root e power x minus 1. Now, this is the idea of integration by substitution. We have special cases of integration by substitution, like this one, integration of 9 minus x squared dx. We don't have a direct primitive rule to integrate this one, so we have a special substitution that will be given in the exam. So it will be, we can take x equal 3 sine t or 3 sine u, whatever. So dx will be 3 cosine t dt. 3 cosine t dt. Now we write the integral in its new form, square root 9 minus x squared, that's 9 sine squared t, and dx will be 3 cosine t dt. Okay, it will be 1 minus sine squared t, 3 cosine t dt. So we have integration 3 out, 1 minus sine squared to cosine squared t, 3 cosine t dt. Okay, it's 3 out there. Square root of cosine squared, it's cosine. Cosine times cosine, it's cosine squared t dt. So how can we solve cosine squared? We can use double angle formula, which is half 1 plus cosine 2d dt. Okay, it will be 3 over 2 by taking half outside. It's 1 plus cosine t 2t dt. Okay, it's 3 over 2. Integration of 1 is t. We are integrating with respect to t. And the integration of cosine, it will be sine 2t, and don't forget we divide by the derivative of the angle half, and you can plus c, and you can take t. We have, from where we can get t in terms of x? From here. We can see t here, or let's take step by step. Sine t is x over 3, so t will be arc sine x over 3. We can substitute it in the solution of the example here. Okay, so it will be 3 over 2t. T is arc sine x over 3 plus half sine 2t. 2 arc sine x over 3 plus c. We have another special kind of integration by substitution. When you can see it, try the given one. Okay. Let's try last example in integration by substitution from our exam last year in Lisbon, given in this form: square root x plus 1 plus 1 over x plus 2 dx. And he gave us the suitable substitution. He said put x plus 1 equal t squared. So let's follow this substitution. By differentiating both sides, it will be dx equal 2t dt. Okay, let's see, or let's write the integral in its new form. It will be square root of x plus 1, square root of x plus 1, it will be t. So it's t plus 1 over x plus 2. X is t squared minus 1. It's very easy. T squared minus 1. dx is 2t dt. Okay? Okay. 2 outside the integral. 2, let's write 2 outside the integral. And t squared plus t, we multiply t by the numerator here, and t squared minus 1 dt. Let's distribute 2 integral t squared over t squared minus 1 plus t over t squared minus 1 dt. Integral t squared over t squared minus 1, we have to solve this one, plus integral t over t squared minus 1, and we need to solve this too. Okay, 2 t squared plus t squared over t squared minus 1. We have a very important technique here. T squared, we can add 1 and minus 1. T squared minus 1. This will solve the first integral. The second one is easy. If you multiply it by 2 and multiply it by half outside, it will solve the integral. Let's see. The first one is equal to, let's distribute t squared plus 1 over t squared plus 1 is 1, minus 1 over t squared minus 1. 1 over t squared minus 1. So minus 1 or plus 1. Here, we have a small mistake. X here, t squared minus 1. T squared minus 1. So it should be plus 1. Sorry, it will not affect most of our calculations. Only plus. Sorry for this mistake. Because yes, it's plus 1. So that's why I write 1 here, because the technique of adding 1 and negative 1 is oriented to cancel the first one, t squared plus 1 over t squared plus 1. It's 1. So by intuition, I wrote it 1, of course. 1 over t squared plus 1 dt plus half integral 2t t squared plus 1. Now, the whole integrals are direct primitives, are ready to be solved, because 2 here 2 outside. Integration of 1 is t minus integration of this one is arctangent plus half. We have the numerator is a derivative of the denominator. It will be ln 1 plus t squared plus c, and you can substitute t by its values in terms of x. This example is one of our examples on last exams. So I'm moving through slides 57, 58, and all these examples are from previous exams. You have to check them very well, and I solved all of them to you. So you have to solve all these examples. And when you if you have any concerns, contact me. I am always here with you. Okay, let's see another example. Let's take this one just to cover most of our ideas. Let's take this one from I think last year or the year before. Integration of sine x over 1 plus sine x. Here we don't have also a direct primitive, but we have a direct substitution. It will be given to you, which is tan x over 2 is equal to, you will have in the exam a table of substitution. This table is already exist in this lecture. If you check the slides, you will see the table of substitution. When you found sine x in this form, you can take the substitution by the half angle, which is tan x over 2 equal to t. And we have an identity, a trigonometric identity called sine 2x is equal to 2 sine x cosine x. Okay, what should we do in this example? So from this one, if it is not sine 2x, if it is sine x as in this problem, it will be half sine x over 2 cosine x over 2. Okay, now let's see. We have tan x over 2 is equal to t. If I have right angle like this one, this angle x over 2, and I'm saying tan x over 2 is equal to t, the given substitution, the tangent of x over 2 is t, so the opposite over the adjacent is t1, t over 1 is equal to t, so it will be, the hypotenuse will be 1 plus t squared. I think you know this very well. Now if we can try to get sine x, it will be 2 sine x over 2. Sine x over 2 from here is 1, sorry, t over square root 1 plus t squared. Sine is opposite over hypotenuse. Cosine, it's 1 over square root 1 plus t squared, the adjacent over hypotenuse. So it will be 2t over 1 plus t squared. Okay, let's write our integral in its form. But before writing the integral in its new form in terms of t, we have tangent x over 2 equal t. We should differentiate the both sides. Now x over t2 is arctangent t. If we try to find x over 2, solve for x over 2, we can write it arctangent t. Now derivative, so x equal to arctangent t. Why did I do this? Because I wanted dx. We have a subject dx in terms of t, so we have to get x from here. So dx will be 2 over 1 plus t squared dt. The derivative of arctangent is 1 over plus t squared. When you integrate 1 over plus t squared, you get arctangent. Now finally our integral will be in this form. We have, if you back to the substitute, so the original integral here, sine x, it will be this one, 2t over 1 plus t squared, 2t over 1 plus t squared. And down we have 1 plus sine, which means 1 plus 2t over 1 plus t squared, times dx, it is 2 over 1 plus t squared dt. Okay, what should we do? What if we multiplied up by 1 plus t squared and down by 1 plus t squared? So we have 2t, and we have here 1 plus t squared plus 2t. Okay, 2 over 1 plus t squared dt. So you can see that 2t here. Here we can see t plus 1 squared times 1 plus t squared dt. It is okay. Now we have a very complicated formula to solve. It will be solved by partial fraction decomposition. What is this? It is our last technique. Integration of using, partial fraction decomposition. At the end of this technique, you will be able to solve these kind of integrals. So let's see how to solve the fractions using the partial fraction decomposition. Okay, the forms of integration by substitution are in page 80, 81, and 80 and 81. Okay, now we will try to understand what is the derivative, what is the primitive of rational functions, or how to use partial fraction decomposition to solve the integrals of fractions. Okay, let's see. We have two important conditions to solve any fraction came to me by partial fraction decomposition, because not all fractions can be solved. If you get this one, 2x over 1 plus t squared dt, oh sorry, not t, it's x squared, x squared dx, it will be ln 1 plus x squared plus c. So it's a fraction, but we didn't use a partial fraction decomposition. So we have two conditions to solve any fraction, or to get the primitives or the antiderivatives of fractions of rational functions using partial fraction decomposition. What are these two conditions? First one, we have a rational function. This rational function is in this form. Before writing the first condition, we have a rational function in this form, b of x over q of x. So this is a polynomial, and also it's a polynomial. Okay, so we have for any polynomial a degree. So to solve the rational function to get the primitive using partial fraction decomposition, we have to check the degree of the polynomial of the numerator and denominator, and the degree of b of x should be less than or equal degree of q of x. If you find that the degree of the numerator less than or equal the degree of denominator, you can use partial fraction decomposition. Here the degree is 1 and here is degree is 2, so we can use partial fraction decomposition, but we didn't, because the second condition is not satisfied. The second condition is that the polynomial b, the polynomial q is a kind of polynomial that can be factorized. Q of x can be factorized, as you see here. Here we cannot factorize, so we cannot use partial fraction decomposition. Okay, now so we have two cases. The first, we have two conditions. First condition, the degree of numerator less than or equal in degree of denominator, and the denominator, the polynomial in the denominator can be factorized. Type. What if I get a fraction that the degree of numerator is more than, like this example, integral of x power 3 plus x power 2 plus x minus 3 over x minus 1. Here we have a polynomial up and a polynomial down, and the degree of polynomial up is 3 and the higher degree of polynomial down is 1. So we cannot we cannot use the partial fraction decomposition, but we will use something called long division. So here we cannot use partial fraction decomposition because one of our conditions, two conditions are not satisfied. That the denominator can be factorized, it's only x minus 1, it's in its simplest form, and the power of numerator is more than, so we cannot use partial fraction decomposition, but we can use long division. So remember with me what long division is. We can divide x power 3 plus x power 2 plus x minus 3 over x minus 1. X power 3, let's check. Many of you don't like the long division, but it's very easy. Let's see. The first part, we will divide x power 3 over x power over x. It's the first one, first step. X power 3 over x is x squared. The second step, multiply x power 2 by x, it will be x power 3. Multiply x power negative 1, negative x squared. Then the third step is subtract x minus 3 minus x minus 3, it's 0. It will always cancel. X power 2 minus x power 2, 2x power 2. This is simply the idea of long division. It will be repeated. Repeat. 2x power 2 over x, it's x. It's 2x. Multiply 2x times x, 2x squared, to be cancelled. Remember, 2x times minus 1, minus 2x. Repeat this example again and again. Repeat the record, because if you don't understand the long division, okay, it will be 3x. We will subtract, so I converted the sign to positive, minus 3. Again, 3x over x, it's a 3. 3 times x, 3x. 3 times minus 1, minus 3. So we get 0 by subtracting. So we have two important terms. This is called remainder. And the remainder, luckily, here is 0. Here is the result, or the quotient. Now, if we divide x power 3 plus x squared plus x minus 3 over x minus 3, we get the result. So we can get rid of all this fraction and write only x squared plus 2x plus 3 dx, and you can already solve this one. This, if you have a fraction that the power or the higher power of the numerator is more than the degree of the denominator. What if the degree of numerator is less than? In slide 86, you can see the forms of partial fraction decomposition. Let's take first example that matches the first case. If you have this problem, and you can see also that 2x over x plus 2 x minus 3, and you can see that this integral is not direct. We don't have direct primitive that if we differentiate it we get 2x over x plus 2 x minus 3. We don't have this one. So what should we do? It's a partial fraction decomposition. Does it match the rules or the two conditions of partial fraction decomposition? Positive, yes, because we have the power of the numerator, the degree of the numerator is less than the degree of the denominator. We have power 2. Second one, the denominator is already factorized, can be factorized. If we, it is in originally, it's x squared minus 6 minus x. So we factorized this one to this. So it's in simplest form. When we found two factors, and then this is the first case of partial fraction decomposition. When we found the numerator, two factors of degree 1, each one of them is degree 1, So what should we do in the first case? We will use the first case. First case called tells us that bx plus q over x minus a, x minus b. It will be if you found in the numerator, in the denominator, two factors of degree 1, each one of degree 1 after factorization, it will be a over x minus a plus b over x minus b. So this is typically like this case. So it will be, forget the integral, let's take the integrand, x plus 2, x minus 3 equal a over the first one, x plus 2, plus b over x minus 3. This is the first case. What should we do? Try to cross multiplication. So it will be 2x equal a times x minus 3, b times x plus 2. What did I do here in this step? I have 2x. When we multiply this here, we can cancel x plus 2 with x plus 2. When we multiply again here with b, we can cancel x minus 3 with x minus 3. So the remaining parts are x minus 3 times a and x plus 2 times b. Now, let's try, we have an equation, but this equation with two unknowns. So let's try x with 3, y, you will see y. 2 times 3, it's 6, equal 3 minus 3, it will be cancelled. 3 plus 2, 5b. So b here is 6 over 5. Now, let's try x. I think you guess what is the next number you will substitute, negative 2. So it will be negative 2 times 2, negative 4, negative 2, negative 3, negative 5a. Negative 2, it's 0. So a is equal 4 over 5. Now we have the new form of our integral in this. A over x plus 2, this is the integrand, a over x plus 2, a is 4 over 5 over x plus 2, plus b is 6 over 5 over x minus 3 dx. Now it's 4 over 5 ln x plus 2 when you solve this this one, and 6 over 5 ln x minus 3. So this is called partial fractions. Partial fractions. We splitted a combined fraction to two or more fraction that can be integrated easily. This is the first case. Let's focus. You will see perhaps, or maybe you will find in the exam an MCQ like this one. Perhaps he will give you an integration, and the choices is the cases of partial fraction decomposition. What should you will use in this integral? I think I have one example here. When I see it, I will tell you. Okay, let's try this example. X squared plus 1 over x power 3 plus x power 2 dx. First, we have the power of the numerator is less than the power of the denominator, and the denominator can be factorized in many simpler factors. X squared plus 2 over, if we take x squared, it will be x plus 1. So we have small factors. We factorized the denominator in this form. So let's back, please. You should open the slide 86. You will find here we have two cases in this one. We have a case, remember the first case is called, if we have bx plus q over x minus a, x minus b, it will be a over x minus a plus b over x minus b. This one, and this case is already here, one of them, x plus 1. What if we have a repeated term? 1, x is degree 1, but it's repeated. X times x squared. If we have a repeated term, you have a case like the second case, x minus a power 2, for example, a over x minus a plus b over x minus a squared. And this we will use in our example. So x squared plus 1 over x, over x times x plus 1, x squared. It will be a over x. Folks, we have x squared. It will be a over x plus b over x squared plus c over x plus 1. Okay, let's solve. X squared plus 1. If you multiply this by this, we will cancel one of the x's, so it will be a times x plus 1 plus b times x plus 1 times c x squared. Let's try x with 0. It will give us 1 equal a plus b. It's one equation. We cannot solve it. We need another one. Let's try x with negative 1. X with negative 1. We will get negative 1. It's 2 equal. This will be cancelled and this will be cancelled. C equal 2. Okay, let's try another one. X equal, say x equal 1. Take a simple 1. X equal, okay, x equal 1. It will be 2 equal 2a plus 2b plus c, which is 2. So it will be 2a plus 2b equal 0. A plus b equal 0. No, I think we don't, it's not right. If we take x equal 1, it will be 2 equal 2a plus c. Yes, c, it will be plus 2. If we put here 1, okay, تمام. X minus 1 will be 2 equal c. It's okay. I think we have something's not right here. Okay, we have a mistake in this one. Let's see. If you multiply this by this, it's x squared. We will cancel one of the x's. I think you may notice this. Okay, so if you substitute by x0, already it will be cancelled and c will be cancelled, so we have b, which is equal 1, and the c equal 2, and when we put x equal 1, so it's 1, 2a, it's okay. b is already 1 here, plus 2, 3, 2, 3, 2 minus 3, but 2a equal 2 minus 3, it's negative 1. Here we substituted by x equal 1, so it will be 2b, so it will be 2. Sorry for this mistake, just the calculations. 2 plus 2, 4, 2 minus 4, it's equal negative 2. So a will be negative 1. So we get the three constants. So the integral will be a over x. A is negative 1 over x. I think you know the integral of this very well. Plus b is 1 over x squared is already easy. plus c which is 2 over x plus 1. All of these terms can be integrated very easily because it will be negative ln x. This is x power negative 2, which is negative x power negative 1 by increasing or raising the power 1. And this is 2 ln x plus 1 plus c. So here we, by factorizing the denominator, we can use partial fraction decomposition. طيب. This one, can we use partial fraction decomposition or not? X squared minus 2x plus 3 dx. No, we cannot use partial fraction decomposition because the denominator cannot be factorized. We don't have two numbers that its multiplication is 3 and summation is 2. We don't have this. We cannot factorize the denominator. So what should we do in this example? And this example is a little tricky. We can do this one. Let's focus. We can say x plus 2 is minus 1 plus 3. And I will tell you now how or why we do this. Here we have x squared minus 2x. What is the derivative of the denominator is 2x minus 2. So if we take 2 common, we have x minus 1. So we just only need to multiply it in the numerator to get the derivative of the denominator. So we distribute x minus 1 over x squared minus 2x plus 3 dx plus 3 integration of 1 over x squared minus 2x plus 3. This is very easy because you can multiply it by 2 and outside by half. Now this is the tricky one. What should we do in this form? Let's forget the first integral. You can solve it. It's a logarithm of the denominator. Let's forget the 3 and let's try to focus on this one. Integration of 1 over x squared minus 2x plus 3. Still I cannot factorize the denominator. So what should we do? We will complete the square of the denominator. How can we complete the square? It's x minus half of this number is 1. X squared, when you try to expand this factor again, x squared minus 2x plus 1. But I need this plus 3, so we have to add plus 2. Again, let's try to expand this factor. X squared, times 2, x times negative 1 times 2, negative 2x plus 1, but I need this plus 3, so we have to add plus 2. Okay. Now 1 over, what if we take 2 common from the denominator? It will give us 1 from here, and this will be x minus 1 squared over 2. Let's try to multiply 2 again. 2 times 1 is 2. 2 times this term is this one. You will see why I am doing this now. Have 1 over 1 plus, can I write this root 2 squared dx? Try to distribute the square. X minus 2 squared, square root of 2 squared, it gives 2. This is the form of arctangent. We have here have, but we should have the derivative of this function. The derivative of this function is 1 over root 2. We should have here 1 over root 2. So we should multiply by root 2. Now the solution of this integral, root 2 over 2 arctangent x minus 1 over root 2 plus c. Don't remember, remember to add this term or multiply this term by 3 because we have forgotten the 3, and add this to the solution of the first integral. So it's kind of tricky integrations. What if, last example in this lecture, sorry for this long lecture, but I'm trying to cover the most of the ideas. Let's try the last example. Integration of x squared plus x plus 2 over x squared plus 1 x plus 2 dx. Now we already have two cases of partial fractions. Let's back to slide 86, and now we have a new one, a new factor of second degree, which x squared plus 1, and we cannot factorize this factor. X squared plus 1, but we already have the denominator in its simplest form. What should we do in this example? We have another case that tells us if we have bx plus q over x, for example x plus a, and another quadratic one that cannot be factorized and of degree 2, so it will be a over x plus 1. This is from the first case, and here the second one, bx plus c, we put in the numerator the form, the general form of linear equation, which is bx plus c. Here of degree 1, up there we put a constant which of degree 0, degree less than 1. Here we have degree 2, so we should put in the numerator an equation of degree 1. What is the simplest and the common and the famous form of degree 1 equation? It's a linear equation, which is bx plus c. طبعا I used b and c, I didn't use a because I already used a before. So the integrand will be written in this form: x squared plus x plus 2 over x squared plus 1 times x plus 2 equal a over x plus 2 plus bx plus c over x squared plus 1. This is how to partial fraction the composition of this. So multiplying the cross multiplication again, x squared plus x plus 2 equal, when we multiply this by a, we can cancel x plus 2, so it will be a times x squared plus 1 plus bx plus c times x plus 2. Let's try x by negative 2 to cancel, or negative, I think negative 2, yes, negative 2 to cancel this term. So it will be by substituting by x with 2, it will be, the left hand side will be 4 equal 5a. So a here is 4 over 5. Okay, try to put x equal 0. X equal 0. So it will be 2 equal a plus 0 here, x, and this will be 0, 2c. And we have a equal 4 over 5, c will be equal, by some calculation, will be 3 over 5. What about b? Put x equal 1, another simple value. It will be 2a plus 3b plus 3c. When you substitute here by 1, it will be 2a. When you substitute here by 1, it will be b, and you have c by 3 over 5. 3 times c, substitute, 3 equal 2a, which is 2, you have a 4 over 5, 2 times 4 over 5, 8 over 5, plus 3b plus 3c, which is 9 over 5. From this equation, you can get b easily, negative 2 over 15. Let's write our integral in its simplest form. It will be in this form. Integral a 4 over 5 over x plus 2. It's very easy to integrate. Plus negative 2 over 15, which is b, x plus c 3 over 5 over x squared plus 1. Carefully have a look to this. It's the form of arctangent. So what should we do here in this form? 4 integral 4 over 5 over x plus 2. We don't have concerns about this one. Now negative 2 over 15, let's distribute integral x over x squared plus 1. It's very easy. You need only to multiply by 2 inside and you have outside. Okay, plus 3 over 5 integral of 1 over x squared plus 1. It's a direct primitive of arctangent. So the solution will be 4 over 5 ln x plus 2, the first one, minus 2 over 30 by multiplying 2 times 15, ln 1 plus x squared plus 3 over 5 arctangent x. This is an important example. When you have a look at the slide of 97, you will see that consider a function of rational function defined as follows: 1 over x squared plus 4 times x minus 2 squared, and you have to choose one of the one out of four partial fractions decomposition, and you will see that it is very easy. We have here a repeated term and we have a quadratic term, so we should have a linear form. So A and D are out of our choices, so we are about AX to B and C. We have a repeated term, so we should have this term, and this term is repeated, power 2. So it will be C. It's okay. And this in 98 we have a long division example. It's very easy, you can solve it. In 99 we have the same example as we solved it before, one of degree 1, the two factors, one of degree 1 and one of quadratic form. And we have in 100, in slide 100, you can see multiple choices of the same form. You can choose the right or the correct choice by studying the cases very well. This is our recorded lecture about the primitive. Good luck, and if you have any concerns, please send me the message or send me an email, and we will and I will see you in the day of the exam. Thanks so much. See you later.